Thank you very much to the organizers, Fedor and Fong and Nadja and everyone here for organizing this conference and having me. So today, what I'm going to talk about is identifying search and stockpiling behavior. The title I made up is experimental and field data. So what I want to do is actually mainly I want to use these two papers to talk about dynamic behavior. When I say experimental and field data, what happened is like in the first paper, which is about identifications of forward-looking behavior in the stockpiling model, that is using field data. The second paper is about search behavior. And in that paper, we will be using, I'm going to be using experimental data, actual experiments. And so it's not like I use both together in one paper. And of course, we can do that as well in some cases. So let me just start with the first one. I want to start with the stockpiling paper first. And it's a don't work with method of one. So now in this paper, one of the things that we really want to focus on is the stockpiling model is something that before us, there are quite a few people working on that, including Ryan Ching and Henry Lieber, these are pioneer works. In the setting of consumer packaged goods. And so you imagine that you need to go and do grocery shopping, you need to buy laundry detergent, or you need to buy breakfast cereals. Sometimes you buy more than toilet papers. Sometimes you buy more than you need for that week. You probably buy it for enough for you to use a month or two. How do we explain people stockpile? This is inherently a dynamic problem because inventory itself is a state variable, right? And the more you have stockpile, the bigger the inventory you have, the longer it's going to last. At the same time, when you approach running out of inventory, you might, increasingly have incentive to stockpile, especially if you see the price is good. And now this is a very important dynamic behavior, but just like most of the dynamic models, most of the papers in the group of works, when we're dealing with dynamic models, we assume the discount factor is fixed. And the literature, and even today, so you see a lot of papers doing that. People calibrate it using the prevailing interest rate. And if you're handling some high frequency data, like weekly data, and the discount factor will be very close to 1, like 0.9995, for example. Now, why would you do that? Now, this is clearly, when we do structural estimation, this is a structural parameter, right? How forward-looking people are. And why are we trying to estimate it? You will hear in the literature, people will give the reasons that non-parametrically it cannot be identified. And this is one well-known result. It's true that if you don't put any structures on the utility functions, the dynamic model will not be identified because, intuitively, every state, the utility function can take different values. You think about CCP, you can, even you have infinite amount of data, but every possible state, you can calibrate the choice probabilities perfectly. Now, in the dynamic model, you have like n states, right, n values of the utility function parameters that you need to estimate, plus a beta. Right? You just don't have enough information to pin down all the parameters. You only have n choice probabilities at most. But once you're willing to put some restrictions to the model, then that's a different story. In practice, actually, when we put utility functions, assumptions, like some parametric assumption, we are already putting some restrictions to the model, and that actually will generate exclusion restrictions. And what we're going to do in this paper is we're going to talk about one particular exclusion restrictions motivated by the institutional setting of a stockpiling model. We want to show how that exclusion restrictions can help us to identify the discount factor. And then after that, we can estimate other parameters as well. So our approach is actually related to Fan and Wang, the same thing that Henning, that's actually Henning, and also Arbring and Bedroy. And then later, there are, in addition to us, there are other papers that attack the same problem. So then we talk about in the context of consumer stockpiling, what kind of restrictions that are natural, that can be motivated by the institutional settings, that can help us to pin down the discount factor. And one clear variable that we can argue is just the inventory variable by itself. This is the most important variable, state variable, that we face in the consumer stockpiling problem, right? And now, how does it help? And now imagine, that say I'm drinking a bottle of water, right? Or you can imagine this is a laundry detergent bottle as well. I start drinking it, inventory drops, right? Inventory drops, but I'm not throwing away the bottle. I'm still holding the bottle. It's still taking up the same space in my bag, right? And so you can see that as I consume, I get some consumption value out of it, right? But at different levels of the amount of water in this bottle, the different inventory levels, it doesn't change the storage cost. Right? However, if I'm forward-looking, it potentially can change my expected future payouts. Right? And that's the ideas behind the exclusion restrictions that can help identify this discount factor. If you can find a state variable, and for some values of that particular state variables, the flow utility, the current flow utility remains unchanged. Okay? But when the values drops, in this case, the inventory drops, your expected future payoffs may be different, right? You may be worried that I'm going to be, finishing this bottle. I'm going to be really thirsty, and I may have a strong incentive buy as a result, anticipating that I don't want to end up in a situation that I don't have anything to drink. Or you can imagine, if you're thinking about buying laundry detergent, or maybe even a better example, thinking about during the pandemic time, toilet papers, you might hear people are willing to pay hundreds of dollars to buy toilet papers. That's because you see out of stocks, in the grocery stores, in supermarkets, and you're really worried about, hey, what if we run out of toilet papers, right? What do we do, right, when you go to the toilet? So that's one example. You can imagine, people, if they're forward-looking, then they become very eager to buy when they almost like running out of inventory. And so this is the kind of exclusion restriction argument that we want to take advantage of. And essentially, what we want to say, is that the insight is that for a large regions of these state variables, the storage cost is flat. Okay, and that gave us these chances to, take advantage of exclusion restrictions, and more precisely, in the context of, let's say, laundry detergents and breakfast cereals, things like that. It may be better to think of the storage cost as a function of the number of packages. Okay? And sometimes, some households may even just set aside some space in the laundry room for storing laundry detergent. You may just set in some space in your kitchen cabinet to store breakfast cereals. And so as long as you haven't hit that capacity constraint, your storage cost, your marginal cost of storing an extra unit is basically zero. Now, you may wonder why people don't look at this problem before. Well, let me see if I should have one bullet point that I will talk about that later. I might as well talk about it now. In the previous literature, what you will see is that like early in Ching or handle Niveau, people usually model storage cost as a continuous functions of inventory. Okay. And this kind of assumptions actually is, from an economist's point of view, is very reasonable, right? Because you want everything smooth. You want to model storage cost as a smooth function of inventory, and they give you, some nice properties. But what we're going to argue is that, sometimes when you make that kind of assumptions, which is seemingly innocuous, that actually can rule out the exclusion restrictions that can help identify the model. In this case, if you have a storage cost in the utility functions, which is a continuous function of inventory, right? What happens is when you run out of inventory, when you start consuming, your inventory runs down, your storage costs also go down, right? So just the storage cost component alone in the flow utility can explain why people become more eager to buy. So the flag regions of the storage cost actually rule out that story. So if we observe people are more eager to buy as the inventory come down, then it has to be attributed to the expected future payoffs. So I'm going to try to illustrate this in a little bit more details. Now I'm going to consider prices fixed, and consumers only has one bottle of longitudinal pattern left, and we want to see what happens as you're more forward-looking, and how does that affect your behavior? I suppose if someone's completely myopic, right? What you will see is that someone's forward-looking, these consumers' purchase probability should increases as inventory drops, even though price is fixed. But for myopic consumers, it will remain, your choice probability will remain flat. Okay. Not until you actually run out of inventory and time, then your purchase probability may jump. Okay, so this is something I can sort of illustrate in these pictures. Now this is a situation when someone has very high discount factor, beta is close to 1, right? And so imagine this is choice probabilities. You plot periods on the x-axis, but in this case, what I'm thinking is that there are 16 inventory units, and in each period, people consume 1 unit. So as time goes by, your inventory drops, right? And so as inventory drops, someone's very forward-looking, their choice probabilities will behave in a way that they will become increasingly more eager to buy. But if you're completely myopic, beta equals 0, okay, then what you will see is that this person's choice probability doesn't respond to the inventories. Okay. Not until you actually get to the point of being run out, then it does. All right. So now we can make things rigorous, and here's a set of assumptions I want to assume for simple illustrations. Here I assume there's a single products available in 1 package size, and the package size is 8 units. And I assume the consumption need is fixed. People just consume 1 unit at a time, and the price is also fixed. There's a price coefficient, there's a stock out cost. So when you run out of inventory, that will create stock out problems that you don't want to face. And discount factor, and the inventory variable is I, and the consumer need to decide whether to buy or not. Simple decision problem. There's no branch choice problem. And assume maximum storage capacity is 3. And the consumption utility is gamma, but I'm going to set gamma equals 0 for simplicity. Okay. So if we just play around with the alternative specific value functions, this is something that you guys should be familiar with by now. You can just write down these alternative specific value functions as follows. So here the first equation is just that V1 is your alternative specific values when you decide to buy. And if you decide to buy, you pay the price of buying this product. And also you pay the storage cost. So whatever your inventory level is, let's say you have one package. Now, when you buy another package, then omega-2 is capturing the storage cost of 2 units. And then you consume 1 unit. So then the next period, when you move to the next period, the state variable becomes I plus B minus 1. That's because you buy one package at B units to your inventory. Right? So I plus B, but then you also consume 1 unit. That's why you get I plus B minus 1. Yes.
So eventually can the last takes need but I thought we really could have that always. There is no uncertainty from what I'm going to need. Why don't I wait until I know exactly what I'm going to run out and I know exactly that day to do very cheaply. So what's this source? We don't get that.
Yeah, so you can still get the dynamic incentive, or you can still get incentive that you want to avoid stock out, because in these kind of models you have this logic error term. So there's always a chance that you can anticipate next period I might get a very negative shock in the epsilon. Just imagine, if we're thinking about, laundry detergent, every week you have to do your laundry. Right? So that's the amount of laundry detergent that you need to use each week.
So the shocks are not
the shock is not changing the needs, but the shock, the epsilon, the IID extreme value error time shock, will somehow maybe just make it less likely that you're able to go to the supermarket to do shopping, for example. Okay. And maybe something urgent happens that prevent you from leaving home this week. And so that's the idea. And so you're right, if the error term is not there, then people should just wait until you run out to buy, right? But in the framework that we're dealing with, right, we always have this random utility term there. That by itself is already enough to generate the incentive for you to try to avoid that kind of, however unlikely situations. Exactly. Yeah. All right. So now then another term is that at the same state variables, I, same unit, and if you decided to not buy, then your storage costs stay unchanged, omega-1, and your next period inventory will drop by 1 unit. So the primary thing is that we take the difference of these alternative specific value functions. We're interested in this because we know this can be represented by the log of odd ratios of the choice probabilities. So these, we just take the difference of the equation 15 and 16, that will lead to this equation 15, right? Now, this is where we can apply exclusion restrictions to help us to get rid of this flow utility. If we assume that there are 2 levels of inventories where the storage cost remains unchanged, right? So I and I plus 1 is 2-level inventories where the storage cost remains unchanged. You can consider apply the same arguments about to I plus 1, right? And then you take the difference of these 2 difference in value functions, then these flow utilities will be exactly the same. And when you take the difference, it will drop out. That will lead to these equations here. And now with some additional manipulations, you can play around with the additional tricks that you have learned in this last few days. It's not too hard to show that you can actually change these value functions expressing in terms of V0 plus a bunch of choice probabilities into these equations here. And then with some one more additional tricks, you can essentially write these equations down to these expressions. Now that would be sort of going back to, I would just skip all this math here and just lead to the final equations here. You essentially can show that there's one moment conditions that can help pin down the paper, pin down the discount factor. And so this is kind of like more mathematical way to think about the argument, the intuitive argument that I just explained. And everything can be expressed on the right side, can be expressed in terms of choice probabilities. But in our original paper, we actually used two exclusion restrictions to help us to get to these equations. But in the more recent proof that I've worked with a grad student, we actually see that you can take advantage of the difference of these two alternative specific value functions. One is the alternative specific value function of choose not to buy, evaluated at I plus B. B is the number of units in a package minus the value functions of the alternative specific value functions of choose to buy at the inventory level I. And when you look at this difference, actually, these two actions and at these two different states will lead to the same end of the period inventory levels. Okay, so when you think the difference actually allows the difference of expected future payoffs. And so in terms of math, it is very helpful. It makes it much easier for us to show that we can get rid of some of the terms that I showed you earlier. And this is inspired by this paper by Kong and Debay and Owen, a working paper, which they also looking at these same problems that we're dealing with now. But interestingly, both proofs are actually dealing with the same moment conditions they can identify data. And then the rest of the structural parameters can be identified in a straightforward way once you're able to pin down the data. Now, I have a few remarks, but let me just pause here for a second and see if you have any questions here. Okay, so now I want to highlight a few things here. Number one is that even though the example that I showed you is assuming fixed price, and even though price is fixed, it is sufficient for this problem, for this stockpiling problem, to generate dynamic behavior. And it is something that, to a lot of people, when they're dealing with consumer stockpiling problems, they might think that price fluctuation is needed in order to have interesting dynamics. Because oftentimes when we talk about, in the consumer packaged goods settings, why people stockpile, it's because people see the price is good this period and they want to save money. And so that's why they want to buy a lot to stockpile. Because they don't know when the next promotion is going to come. Okay? But in this framework, I think it's very important to emphasize that price fluctuation is actually not needed. Even though price could be fixed, we still have a stockpiling problem to consider, okay? As long as people are forward-looking. Now, there are a lot of consumer packaged goods market, we see price fluctuation, things are on sale from time to time, but that's not always the case. For example, Walmart in the US, it's commonly used everyday low price strategy. So they set the price for most of the products to be the same across time. And so that doesn't really give the price fluctuation. It's not the reason why people go to Walmart and will stockpile. But price fluctuation does generate more incentive for people to stockpile. So even, so what you will see is that when people do actually estimate the model, when we apply this to the data, we're going to actually consider price is fluctuating. We're going to have to model the price process, and that would give us even more identifying restrictions to help us to pin down the parameters of the model.
Sure.
Yes.
In the simple setup that you just showed, where's the stock out column?
Uh,
Do you see it in the utility function? Or is-
so you will see it. I just didn't show it. Yeah. So in this
In this one,
I didn't show it because I'm considering we are not at the stock out situation. Okay. So when you play around with these arguments about what regions of the data that you need in order to identify the discount factor, you do not have to get to the point when you stock out. You don't need to look at the choice probabilities that you are stock out to help you identify this discount factor. Okay, the most important thing is that we are in some ranges of state variables, okay, where the flow of utilities remains unchanged. Okay. And so that so at least at the point of getting the discount factor, that particular state is actually not needed.
but when you say that the choice probability, the probability of buying the new unit, right, package increases, intuitively you would think that if the stock out cost is high, then this probability would increase faster as you approach.
Yes. Yeah, so it is, it certainly is embedded in the choice probabilities, right? And what I'm saying is that because you don't need to actually observe that state choice probability.
I agree with that.
To identify, to create those arguments to identify this discount factor.
Yeah.
But of course, it plays a role, right, in there. Choice probability is a function of all the structural parameters of the model, including the gamma, right, in order to stop those. Any other questions? Okay, so now I want to move to applications of these arguments. And in this paper, we apply this our arguments to the scanner data. And for some of you who are not familiar with this data, this IRI scanner data is actually very reasonable. You pay only a few $100s, you can get the whole data set. However, it's a little old these days, but very similar data is also available from AC Nielsen's. And they work with Chicago Booth and make the data available to the public for the researchers to use. And some of the universities may actually even subscribe to institutional license. So if your university have it, you may be able to get access to it free of charge. And now we use the IRI data, and our data set is also made available through the replications package as well. The data lasts for 7 years, from 2001 to 2007, right? And now we use the first 4 years data to help us construct the initial inventory. And then we use the final 3 years of data for estimations. We also set the selection criteria that each household will have to make at least 5 purchases in order to make it to the data set. So, and with a little bit of other additional criteria that lead us to only have 312 households in our estimation samples. And now when we estimate these kind of models, when you actually put this model to the data, it's actually much more complicated than the setting that I just talked about, with just one package, with just one brand. When you have multiple brands, in this case, many brands for laundry detergents, and then each brand carry a couple of different package size. And you can have a lot of prices to keep track of. And when you think about an inventory variable, this also can be tricky, because if someone buy a few bottles, someone try to store a few bottles of laundry detergent, right? Then how do you keep track of which bottle people are using? Right? So now in our paper, we try to take that into account. Now we think about making some strong assumptions about the first in, first out, like order of entries. The first bottle you buy, this is going to be bottle they're going to use first, and all that kind of assumptions that we make. It would significantly increase the state space. And in addition, we also have to keep track of price index. So we have to also make some other assumptions to handle that. So all these things can be quite challenging. So in terms of execution, we have to make some simplifying assumptions. And now, one of the assumptions that we make that simplify the problem, the first one is the consumption rate. And in the previous work, like early in 19, Henry Neville, people assume that consumers have random consumptions needs every period. Now, one thing that we do differently is that we calibrate the household level consumption rate. And instead of estimating the random distributions, which are calibrated from the data, and we assume in our setting it's fixed. It's fixed every period. It's a simplifying assumption, obviously, but it actually buys us a lot. And this way of calibrating the consumption rate also gives us some advantages. So how do we calibrate it? We calibrate it by looking at the total amount of quantity that consumers purchase during the sample period, during the 3 years period. We add it all up, and then we divide it by the total observed weeks of this individual. So essentially, assume that everything you're buying in these 3 years, you use all of them. And so that's like the average consumption rate. Now, of course, people may fluctuate a little bit. We make a somewhat strong assumption and say this is a consumption rate that's going to be fixed in every period. But it has 2 advantages. One is that now the consumption rate is household specific. It's individual specific. And unlike when you do it like in early 19 or Henry Neville, when they assume consumption rate is random, they make assumption about one distribution. They assume it's homogeneous across individuals. Now we can actually just look at individual behavior to help us to pin down an individual specific consumption rate. And that could be a major source of heterogeneity of behavior. And another thing is that once we make an assumption that people's consumption rate is constant over time, and in the case of laundry detergent, that's pretty reasonable. Once we make the assumption, now we can impute the inventory variables. And in the past, when you have random consumption rate, the inventory variable, in this kind of consumer packaged goods data set, although we have very good information about what people buy, how much people buy, and the prices, all these kind of things, we don't directly observe inventory. And so when you have that kind of situations, and you have random consumption rate, the inventory variable is unobserved to the econometricians. And we will have to integrate it out. That would make the problem even harder. Yes. Well, in the data, you see fluctuation. That's because you see the price promotion as well. Okay. So, but if you take the price promotion into account, then and if you detrain the price as well, and then more or less this model, I think most people, when they estimate this kind of model, they are basically imposing stationarity assumptions.
So are you observing all purchases from the household, or or people go to other shops?
So good questions. You only observe the purchases in this data set.
Yes.
Okay. Which covers a very good percentage of shops, grocery shop in the US. So this is the standard problems that people will face when they use scanner data. It may not be 100% purchases that they are able to get, because some people may just buy it in some pop and mom type of the grocery stores that is so small that is not in AC nuisance data. But by and large, I think it covers most of the purchases. Any other questions? Okay. So once you're able to sort of also impute the inventory, you have the individual consumption rate that also help you capture or control for the individual unobserved heterogeneity. That actually, these are, in my view, is big advantages. And now there are, different package size. We have 5 different packages, and if we allow for some flexible storage force functions that can, again, increase the number of parameters we have estimated. Also, it's a very much of a pain to keep track of the inventories as a function of different package size. Now, in a version of the model in the appendix, we did take a pain to implement a versions that would track the inventory orders and track different package size. After we estimate that model, what we find is that the storage costs are actually very close to zero, okay, for most people. And so in the paper, in the main text of the paper, we decided to just implement a version of the model where we set the zero storage cost to be zero until you hit certain constraints. And now that assumptions would dramatically simplify the problems, right? Once you make this assumption, you no longer have to track the inventory as a function of the order of the packages that you purchase. So these are the sort of nitty-gritty details that we have to assume when we execute this model. Let me see what else we have. So we also make some assumptions that is similar to handle a niveau, and that's come down to the how do you handle different brand specific preferences, and also how do you track the brand specific prices, so we use the handle a niveau these days in it's totally famous or well-known the inclusive value sufficiency approach to help us simplify the state of space. Now, when we come down to estimating this model, we use Bayesian estimation method. So this is an approach that is proposed by Imani, Jen, and Ching, for others. So this method has the advantage that you can allow for unobserved heterogeneity, in the sense that continuous unobserved heterogeneity. So some of the methods that you have learned from the past few days will allow for a finite number of types of consumers, but when you're dealing with discrete choice problems, sometimes to estimate heterogeneous choice problems, they allow for continuous unobserved heterogeneity. This approach using Bayesian estimation approach has the advantage of allowing for that. So now I won't spend too much time on that. Fine. I think I'm gonna. I won't get into the details of it, except that I will just point out that this approach will. How does it cut down the computational burden? It basically think of the problem as follows. When you dealing with the we have an outer loop and inner loops. When we look at the inner loops of the problems, instead of solving the expected future values or the fixed point of the value functions exactly in each iterations, what it does is it takes advantage of the fact that value functions all the time is a continuous function of the state of the parameter space. So we could potentially use the class value functions that we have already evaluated. We can store them. And when you get to a trial parameter vectors, what you would do is look at the past memories, retrieve the value functions that are evaluated at different parameter vectors values. And the ones that is closer to the one that you're currently looking at, you're going to use that to help you to form an average, an estimate for the value functions. And another trick is that you don't actually solve the value functions exactly. You will solve it partially during this estimation process. But every time when you get to a particular vectors of the parameters that you try to evaluate, the value functions, you will just try to reiterate the Bellman equations a couple of times to help you improve the precisions of the approximations. So this kind of approach, in each step, it helps you to dramatically cut down the computational burden, and also help us to sort of use the information that we have evaluated in the past in more efficient manners. So the idea is that, why do we have to, every time start from the scratch to estimate the value functions if we already have a bunch of value functions that we have solved in the past? We can use them to help us form an estimate about the value functions that we are currently intercepting. And so now we apply this method, we estimate the model. What we found is that for the models that we estimate the discount factor, it produce a better fit than the version of the model when we fix the discount factor at the conventional values. And here are the results. We allow the price coefficients to be heterogeneous, the stock cost to be heterogeneous, discount factor to be heterogeneous. What you will see is that the average of the discount factor is 0.71 in our approach. We have the median values at 0.94. And so it's actually very heterogeneous. If you plot the estimate of the discount factor, you will see that it has a huge range. It ranges from close to 0 to something close to 1, right? And the average value, as I said, is 0.71. And so what have we learned from this? Number one, this contract is pretty heterogeneous. The average estimated value is 0.71. Now, this is weekly observations that we're dealing with. And so it's much lower than the standard calibration approach when we use interest rate. The standard approach will calibrate it to something like 0.9995, right? So what does that mean? Right? What does 0.71 mean? Why is it so low? Oftentimes when I presented this paper in the past, where people will come and tell me that that can be right. This time factor is so much lower than what we typically believe. But when you think about it, 0.71, it means that consumers plan weeks ahead in these dynamic problems. When they buy laundry detergents, their planning horizons is more or less a few weeks before. Now, if you set the discount factor as 0.995, what it means is that when people buy laundry detergents, they're making plans that years ahead of them. Okay? So, you can decide which one is more reasonable. Right? You ask about your own experiences. When you buy laundry detergent, do you plan weeks ahead, or do you plan years ahead? Okay. Hey, that's true. I'm not ruling that out. So there are definitely people who are very savvy, right? So that's what the estimate says. But I think the lesson is, what I try to say is that, first of all, it's all over the map, right? We see a lot of heterogeneity there, and maybe that's not surprising either, right? And what I'm trying to justify is that maybe just setting it for 0.995 for every possible context, it may not be a great idea. It may not be the best idea, right? And in the situations where we could potentially try to estimate this kind of factor, we have the theoretical arguments, we have exclusion restrictions that we can justify using some institutional settings, right? Now, you can always make some assumptions about the parametrics form of the data functions. You can always make some assumptions about the storage cost functional form. And in fact, once you make the assumptions, right, you can also try to estimate the discount factor, because you will get exclusion restrictions as well through that functional form. But the lesson that we want to point out is that we shouldn't just make any functional form assumptions out of convenience. Right? Oftentimes we make assumptions like quadratic storage cost out of convenience. And but if there are some institutional settings that teach us that it could be flat, right? And imposing that maybe is a reasonable way to go. That's my thought. Any other questions? Yes.
Your method of constant of some of the X-rays. Sorry, yeah, so in that, because I think a lot of these might be not far. How to sort and how far from stores they are. So very far, they go once per month. That's what very urban, go downstairs.
Yeah. Yeah, so we didn't explicitly take that kind of, if we have those information, we could incorporate it, we model it as a part of the observable heterogeneity. Yes, so I think off the top of my head, we definitely have a parameters we call it the cost of purchase, a fixed cost of purchase parameter. And there, I think we also allow this fixed cost of purchase parameters to be, let's see, see it here. Yeah, this fixed cost of purchase parameter, we also have some heterogeneous there. And so that would capture the kind of story that we said. So now I want to just show you, okay, so after we get done with this, what can we do? What else can we do? Well, we can do some kind of actual experiments. And here what we basically showing you is that, just to show you, using the standard models, those white two columns are from the standard model versus using a model that we have estimated, that we estimate this kind of factor as well. When we do counterfactual experiments, for example, increase the promotional depth or increase the promotional frequencies, how that may affect the result, how that may change the result, right? So to be more precise, what we do in this table is that we consider 100 ounce type bottles. We put, when we do the increased promotional depth experiments, we essentially cut the promotional price by half, so double the discount. And for the promotional frequency experiments, we double the deals. That is, for the periods when there's no discount, we randomly assign some of those observations to the promotional periods. And now this is what we plot here, what we stated in this table are the changes in quantity demand and also the changes in reference. And what we see is that, just highlight the promotional depth results, what we see is that in the case when you fix the discount factor at the conventional values, basically everything is got a little bit overestimated or overpredict. And so we can sort of play around with different things and to see to what degree it really matters. So I want to just make sure I have some time for another paper as well. So I'm gonna I'm gonna go into yes. Okay, great.
14.
Yeah. Now, any questions? So let's have time. All right. So what do we learn from this exercise here? So which shows that it's a scan factor. In this consumer stockpiling models is identified. It's highly heterogeneous, and the average value is much lower than the standard calibrated values. And now this identification can be achieved if we model the storage cost more realistically. So this is really the key lesson that I think we learned from this study. And in this case, the storage cost is flat, which is oftentimes the case, but not always the case, right? We consider laundry detergents, bottled waters, and things like that. That may be reasonable, but if you think about canned food, right? You buy one canned food, you probably just consume the can. entirely. And so that in that situations that these arguments may not apply. And so one has to be careful when they think about in the context that you're dealing with, whether this is something reasonable to do or not. Now the previous literature has imposed smoothness assumption on storage cost, okay, and assuming that it's continuous in the inventory. That's something that's commonly done, it is similarly innocuous, but it actually rule out exclusion restrictions. So I think one takeaway that I hope you can have is that when you model a problems, try to think outside the box, right? Don't let the existing assumptions that people have made or literature have made, even the papers are very famous, don't let that bunch you. Okay? Just think about more carefully, are all these assumptions reasonable? And think about the real world, think about your own experiences. And I bet it's not too hard for you to come up with some assumptions, some relaxations of the existing model features, which is reasonable. It may not be kind of like natural for you to make those assumptions, because handling a step function, storage cost functions actually can lead to a lot of challenging problems too, right? And but they can buy you a lot in terms of identifications. Okay. And now for the estimation method, I'm going to spend too much time on talking about it, but if you're interested, you can refer to the original paper and also another paper that we wrote, published in QME in 2012, where we named about talking about how to implement that estimation approach. And now, with the remaining time, I can switch the gear, talk about another project. Any questions up to this point? Okay. So now we're gonna switch to another paper where we're really actually using experimental data to conduct the exercise here. And hopefully this fit the theme of the conference of the dynamic social school for this time. And then the focus on this is about search. So let me just motivate this by showing you the following. This is one screenshot from Spotify, and it shows when you go to Spotify, open the first page, it shows the list of artists, right? And you look at it, you pick one of them, and you want to sample some songs or listen to some songs, right? And in some cases, you might know who the artist is. In some cases, you may have no idea what those artists are. And this is another example, which is Google, the hotel search. And when you just look at the searching hotel in a particular locations, it will list a bunch of hotels to you. And now the way they list hotels is not random. In this case, actually, when you see the red square, you will see that it's highlighting the number of reviews, right? So that's sort of indicating the demand. The more people use this hotel, it's actually get ranked, it get displayed higher, it get a better positions. And so how do people search? Right? There are two things that are stand out here. One, the position probably matters. Right, the higher the position, probably you would tend to be reading things from the top to the bottom. So if something listed on the top, it's more likely to get checked out. But at the same time, another piece of information could very well matter as well, like these things that I put in the square. That's the number of people who have used this hotel or left a review before, right? And oftentimes people may think, oh, the more people who have left the reviews, the more likely that this is a good product, right? You might take that as a social signal. So there are two things that matters here in this example that I showed you. The position may matters, okay? This popularity information may also matter. Right? These two things will enter a decision problem of somebody will try to figure out or try to search which hotel is better for them. And now, with this in mind, there's, and you also see that in this example, in the Spotify case, the way they display the artists, they didn't show how many people download the songs, right? They didn't display the information about popularity. So it's not always the case that people do this, display things in this way. And there's also questions about, look at this example. This is what we call matrix format when you display the products. And this is a column format. So there's different ways you can play around, right? As a platform, how do you want to show the products to people? Is it a matrix or column format? And when you display the products, do you want to sort them by popularity or not? Right? Although more commonly than not, when you look at the products being displayed along with the popularity information, oftentimes the products that rank high are the ones that are the most popular. And so the question that we want to ask is, how can we sort of understand consumer search behavior better so that when we advise the platforms, we are able to tell them, hey, which particular display format is better for you. Okay? And oftentimes actually depending on the objectives of the platform, whether they want to maximize the consumer's welfare or they want to maximize their own revenue. Okay? And so now to answer these questions, it's very important for us to be able to measure two things. Okay? How does the product positions, in what degree it matters, consumer search decisions, and also the popularity informations, how much the social influence information matters to people. But this is challenging because when you look at this, oftentimes when you have popularity information displayed, the popularity information and the ranking or the positions of the products, they are highly correlated. And so if in the data we see more people click higher regency dollars, the data doesn't quite tell us, is it because people pay more attention to the position or people pay more attention to the popularity of information? Okay, we have this identification problem there. And so what we do in this paper, the exact research question that we want to ask is, can we disentangle the position and social influence effect? Okay. And the way we're going to address this problem is we make use of field experiments. Now in this field experiment, there are two groups of subjects. One group of subjects is called independent group. And the songs that they're being exposed to are randomly sorted without popularity information. Another group is social group, and we call it social group because the songs that are displayed are sort of based on popularity information. And so how do we take advantage of these two groups? Well, in the independent group, because there's no popularity information involved and the song is sort of randomly, when we estimate a structural models using the data from the independent group, it allows us to pin down the position effect, the product position effect. And the social group has both things in place, but once we estimate the position effect, okay, we can fix the position effect, okay, and then apply the models to the social group, and then estimate using the data from these social groups, holding the position effect fixed, and then estimate the rest of the parameters, including the popularity information parameters. And that will help us complete all the parameters that we want to conduct. So this is the two-step estimation procedures we want to implement. Now, what is this experiment? Let me just be more get into the details of it. This experiment is actually not run by us. It's a large-scale experiment that's run by another researcher. His name is Ching. And this is an experiment. This guy is actually not an economist. Okay? He's a sociologist. He's a very well-known sociologist. He won this experiment many years ago. In fact, in 2006. So I'll show you what the experiments look like. What he does is, he called this music lab. He created his own platform. And in this experiment, he recruited 10,000 participants. This platform has 48 songs, 48 unknown songs. These unknown songs are played by artists. They still often, they're very new artists. A lot of people don't know about them. And the songs is something that you have never heard of. So they will have these songs for people to choose. And they have 3 experiments. And these actually 3 experiments that were used. In experiment 1, they will display the song using matrix format. In experiment 2 and 3, they display the song using column format. Now, for the moment, I want to focus on the experiment 2 and 3. And now in each experiment, there's one independent group and certain social influence groups. And participants are randomly assigned them. So let me show you the experiment 2 and 3. So in some sense, the experiment 2 and 3 are actually very similar to the social influence group in experiment 2 and 3 are very similar to that hotel search page that I showed earlier. Okay, so they will display the songs, and those songs will show along each songs. There's a popularity information that shows how many people have downloaded these songs before you come. Okay. And so the exact way it works is that when subjects come to this platform, put it on the website, and anyone can go to that website anytime they want. The subject will be randomized to either independent conditions or social influence conditions. And so if you are randomized to the social influence conditions, then you get further randomized to one of the world, okay? One of the social influence group. Now, although this is run by sociologists, but Psychiatric is actually I think it's very well designed. What he wants to do is that, he doesn't want to just compare one independent group with one social influence group. He's worried that, even we look at the social influence group, the behavior there, okay, may just happen to be random. It maybe just happen to have some, very strange behavior there. And that's why he wanted one and parallel world. All of them are independent, right? They're independent by itself, but they're all subject to those social influence conditions. Okay? Essentially, this guy actually understands sampling errors. And so he wants to have a number of worlds, and if the evidence that all these worlds show very systematic behavior that's different from the independent world, that gives them information about social influence matters. Now, this research, let me keep describing what this experiment does, and then I'll say a few more words about what the original purpose of this experiment is trying to do. So in this experiment, each subject can sample as many songs as they want, right? And they can sample the entire song or just a fraction of it. And they can download any songs, but they have to sample it first. Now you may wonder, why not download all of the songs, right? Well, remember this experiment is done in 2006. And so at that time, internet is pretty slow. So although all of these songs, you can download it for free, it takes time to download it. Okay, so I think on average, people at most, well, there's some crazy guys that will download all the songs, but most people will download maybe less than 7 songs. Now, what does it look like? So if it's an independent group situations, the songs will be listed like this, right? It's just randomly sorted. When someone calls in, but when they see these songs, decide which one they want to click to try to sample. All you see is the name of the songs and the artist who perform the songs, and they do make an effort to ensure that all the subjects have no idea what these artists are. They never listened to this song before. the social influence group will show that when you log in, these songs are ranked based on popularity, based on the number of downloads prior to your and so let's skip the matrix format for now. So that will be the setup, right? And so you can see that independent group is something that is free of the social influence. But in this group, both the position and the social influence will matter. Now, what is the original purpose of this research, of this experiment? I mentioned that they collected data in 2006. Now, once again, it's really interesting is to try to understand if there, really these things about social influence in the real world, right? Can a song be successful just because of being lucky? That for some reason more people click it, download it at the beginning. That leads to the song being displayed high and show that more people download it. And that by itself would lead to these songs to become successful. So it can be just lucky at the beginning. Then the songs become popular. Or, of course, another force could be that people truly able to figure out the information, figure out which song is the best, right? And in that sense, the social influence information doesn't matter. So it has a very simple hypothesis test. And the way they test it is that just look at the Gini index of the number of downloads as the dependent variable. And what they are basically arguing is that if they find that the Gini index is high in the social influence group, that would suggest that this social influence, this peer effect matters. But they make no attempt to understand the role of product positions and social influence in consumer search behavior. But when we look at this data, when I look at this data, the first one discovered this data, I just feel like this is really amazing data. And this is kind of like data that you would only expect if you work at a company that you have access to. Right? It tracks how an individual sample a product and whether they actually purchase it after sample it. Okay? And then how do they move to the next product to sample if they don't like it? Right? It is kind of the every step of search behavior that's being recorded in this data set. So it just strikes me as a surprisingly detailed data set that allows you to look at consumer search in a very detailed way. And it also provides us a very nice setting to help us to disentangle the product positions and also the social influence of them. Okay. So let me just show you some of the stats. So if you look at, for example, the figures down here, right, and you look at the click-through rate, which is basically sampling rate, as a function of positions, you will see that in the higher the position, the more likely you will try to sample the songs. Not surprising. But when you look at the conversions, right, that is after you sample the songs, what is the probability that you actually download the song? When you look at this is actually pretty flat. So this position suggests that it will actually might play a role in getting someone to sample the songs. But after you sample the songs, whether you actually download or not, doesn't seem like it matters too much. Okay. So when we try to think about these problems, we write a search model, and we want to use the search model to help us to better understand, how the positions and social influence works affect people's search behavior. So here we are basically modeling a few things. So first is the utility of all the realized discover price, right, which is a vector of this XS, and essentially the sum of, right, it's the sum of the The boys down here is the square root of all the songs that we discover as something high quality minus the cost of searching. So when you decide whether you want to sample the songs or not, it depending on your perceived probability that whether the songs that you're going to sample is something that you're going to like. And it's a very simple setup. If you like the songs, you will download it. And if you don't like the songs, you don't download it. And there's a cost of opening the box, there's a cost of sampling the songs, and we put some concavity to the utility functions. So the more songs that I downloaded, then the marginal utility of the extra songs that the extra high quality songs will matter a little bit less. And in terms of the selection rules, we can actually rank the songs based on the ratio between the perceived probability that the next song that you sample is going to be high quality divided by the search cost. And the search cost, we will naturally model this as a function of the positions of the songs being displayed. So the stopping rule is that after finding k high quality of songs, the individual will stop at box J as long as the following is satisfied. And this essentially just boils down to the marginal benefit versus marginal cost. If you believe the marginal benefit of sampling the next songs is higher than the expected, if you figure out the marginal expected benefit of sampling the next songs is higher than the cost, then you go ahead and sample. So we have, again, 48 songs and exactly when you decided whether to sample the next song or not, you form up perceived beliefs about whether that song is going to be something that you like or not dislike. So we have a cost component of the search. In this component, it's going to be a function of the positions. And we also model this in the subterm as a function of some observable characteristics, age, gender, and internet connections. Okay. So in the old days, when we talk about internet connections in 2006, it's actually about whether people use dial-up or not. Okay. So really, it's a very old technology there. Like when you look at the utility functions, again, we allow this to be concave, and there are a couple of components here. The perceived probability of liking the songs depending on a few feedback, appeal, and popularity. Okay. Now, what is feedback? The way we model feedback is it's not in a Bayesian updating way. Okay. This is in the comments I talk about another paper whether how people update beliefs, where we found that people using Bayesian rules may not be always right. And here we're actually modeling this feedback as a way to capturing people maybe doing some sort of adaptive learning. Okay. So it's a very simple way to set it up. So essentially, this is the total number of songs that you have sampled the tensor to be positive minus the number of songs that you have sampled the tensor to be negative. So that's the net gain divided by the total number of songs that you have sampled. So what you're basically saying is that the more percentage of songs that you have sampled turns out to be something you like, you might anticipate that this platform is storing some songs in general match your preferences well. Okay. And you update your belief in this way using this feedback loop. Now, another variable that I have here is appeal. So what does it capture? This appeal is capturing the idea that when someone just look at the songs, the name of the song, the name of the artist, even though they have no idea what the song actually is about, but just look at the name of it, the name of the band, sometimes they give you some ideas about whether this is appeal to you or not. Okay. Now, how do we actually model that? Well, remember, we have an independent group. Right? The independent group does not have popularity information. It just shows the songs randomly to the participants. And so from there, we can actually just look at the raw numbers of downloads from the independent group, right? And use that as a way to approximate the appeal of the songs. And the probability is something that I don't think I need to explain anymore. This is just the number of downloads for song J that participant I observed at the time when they log in. Now, by the way, what happened is once you log in, the probability fixed during your sessions. Even though there may be in parallel, there's some other participants also playing this, going to this platform at the same time, they may be downloading the songs, but for you, once you're in, okay, the probability information that you see is going to be fixed. Okay? But when people enter the platform at different point of time, they will see different probability informations, even though they are being assigned to the social influence group. Right? Okay, so here, what are the exact assumptions that we make? Now the probability feedback, all these variables, we assume that the only affected is the probability of match and also the appeal. And we assume the position, the product position event, only appears in the search cost functions. And now we feel like this is the first kind of reasonable cut to model it this way. But even if you include the position effect in the perceived probability of the match, I think there's no problem for us to implement the two-step estimation procedure that I explained at the very beginning. So the probability, I will explain this, probability remains unchanged. The feedback essentially is one way to kind of model adaptive learning, something that some of the papers in IO these days have started modeling it. In one paper that I've seen on Lee and I, where we actually presented at this conference a few years ago. And so we're going to estimate a model. I'm going to show you the two-step procedures, and we'll focus on the right side of the panel. Now we have an independent group, right? First step is just apply the independent group data using those data sets to estimate the model, and we're able to estimate the position effect along with other parameters of the model. But because the independent group does not have probability effect, we leave this one off. And then now in the social inference group, in the two-step procedure, this column two-step, this is where we apply, holding the parameters from the search cost function fixed. Okay. And then we estimate the search predict parameters again. So that's how we get all the parameters. Now we also try to estimate the model using one step. That is just look at the social inference group and then estimate all the parameters together. Now what happens is when you do it this way, you see that in this case, the position effect is significant using two-step, but when you do it one step, the position effect is no longer significant. Okay? And the probability actually becomes to carry a bit more weight than before. So this shows that, this kind of like multi-collinear problems is going to make it harder for us to identify the position effect. Now I think I have a bit of time, so I'm going to mention the matrix format. Actually, is another interesting things that this experiment shows. The way they run the matrix format is that we go back to the matrix format. The matrix format experiments in the social inference group, they display the probability information. For what happened is they actually also randomize the position of the songs. Okay? And so the matrix format by itself actually give us a very nice setup to try or to validate these two-step procedures versus the one-step approach. Because in the matrix format, the social inference group, because the songs position are being randomized, but at the same time, they display the probability of the information of the songs. You would expect, doesn't matter when you apply two-step or one-step approach, it should give you more or less the same answers, more or less the same estimate. right? And so that gives us a nice way to validate the two-step approach. When we do it separately, we indeed actually get something very similar. We look at the position effect, they're very close to each other. When you look at the popularity effect, they are very close to each other as well. So what is the main takeaway here? Takeaway is something I already mentioned. The matrix in the column format approach, the two-step approach is necessary. Otherwise you may get the popularity effect being messed up. And in the matrix format, because there's no these confounding problems there, it doesn't matter whether you do one step or two step, and it's as expected, we get more or less the same answers. Now we're going to move to with all this, all these estimation results. Now we can move to talk about the counterfactual experiments. So what kind of counterfactual experiments can we do here? And as I said earlier, the platform, if you think about in this case, from the platform point of view, if they run experiments like that, they learn all these parameter estimates, what can they do with it? Well, they may be interested in playing around with different way to display the song, different way to rank the songs, right? And different way to displace or disclose the popularity information. How would they change different outcomes, right? So we conduct 4 different experiments. One is songs are sorted randomly and there's no popularity information. Another one is songs are sorted randomly but with popularity information displayed. The third one is songs are sorted according to display popularity information. And the last one is we're actually able to sort the songs individually based on each participant's predicted download likelihood. Okay? So that's something we're going to try to do. And the one challenge of doing the counterfactual experiments is that when you play around with the different way to display the songs, right, you will end up having a situation that you might, in the model, the consumers, the subjects might try to pick a songs that they have never listened before in the sample, in the data. Right? And in that case, we need to predict to what degree this individual will like the song, right? The likelihood that they will download it. And in the data, we actually does not observe that information directly. So we need to create another models to help us to predict the download probability. And this is where we're actually bringing some machine learning techniques. We decided to, instead of just running a logic model and using a logic model and to put observable characteristics of songs to predict whether someone will like it or not, we run these neural networks. It's called content-based filtering. And we also use another sentiment analysis of software to help us to get the songs in and then let the algorithms to tell us a bunch of characteristics of the songs. Okay? And so in this way, we're able to get a lot of features of the songs. And the content-based filtering essentially allows us to create a very detailed profiles about what kind of characteristics that these individuals like based on the songs that they have decided to download in the data. The content-based filtering is able to just look through all the songs available and try to find the songs that are closer to the songs that you like, and then predict that those are the songs to what degree you would like it or not. And so we use these machine learning techniques to help us to make predictions about, to what degree people will download the songs in the counterfactual situations. So here's the result. We have 3 metrics here. One is the number of downloads, and the number of samplings, and then one's the number of downloads, and then one is search efficiency. So search efficiency is essentially just the number of downloads divided by the number of samples. So this is kind of give us the idea that, hey, how many trials you have to make, how many songs you have to sample in order to find the right songs for you. Right? So the higher the number, the better it means. And so what do we get here? For example, look at the column format. you look at all these 4 experiments, and you will see that in terms of the efficiency, right? The column from the experiment 4 will give you the highest efficiency, right? And experiment 3, which is basically solving sum based on popularity, will give you the second highest efficiency. And so from the consumer welfare point of view, counterfactual experiment 3 and 4 seems to be better than other setups. But you might have different criteria about how you want to operate the business. And sometimes it's not just about giving consumers more what they want. Sometimes when you run this kind of platform, you may be interested in having people just hang around this platform longer, right? Because you may be just running this platform using advertising to get revenue. And in that case, Spotify, some of the models are doing that. And in that kind of situation, you might actually want more people to sample the songs. And the longer they hang out, the better for you. And so you might discover that, hey, counterfactual experiment 2 shows that people will sample songs more, right? This could be your preferred models. And so it really depends on your metrics. And I think I'm almost out of time. Okay. Now, what do we learn from here? The one thing we learn is that we can take advantage of experimental design. In this particular case, an experiment wasn't initially designed for the purpose of learning search behavior, of disentangling positions and social influence effects. But when you look at them more carefully, oftentimes you may be surprised what you find. And you might be able to see that the data not designed for that initial purpose can actually give you a lot of information. And in this particular case, it allows us to learn a lot more about how consumers search. Now we have 2 learning points here, 2 particular conclusions. One is disclosing social information using random assortment will lead to higher sampling rate, but disclosing social information using sorted social information will lead to the highest download rate and search efficiency. But another more general point I hope people will take away from this is that experimental data can often allow us to learn much more than a simple DID design. Okay? Now, the simple DID design, of course, when you want to experiment, you conduct the experiment, maybe that's what you have in mind, right? That certainly will be something we can learn a lot about. But if you combine it with a structural model, in this case, we're not even doing full-blown structural model. And the search model that we're doing here does not take into account that people may be forward-looking, people may be actively doing those exploitation problems. And so there's room for us to do more, definitely. But even just a simple search model that we're considering, we're able to learn a lot more than what we normally cannot do when we look at those clickstream data. And now there are more examples that are in this nature, like Penn and Hamilton, and one has a paper, it's called all presented at the conference, that also make use of randomized clinical trials data to and combined with structural models to help us to improve our understanding. Okay? And here's another paper by Misra and Nair, and look at the sales force dynamics and when they face different compensation schemes. So that's something I think could be very useful for you to consider. And on other times, I'm going to stop here. Thank you.